In this module, you'll get a high-level first look at Huawei's Ascend 910C and 950 NPUs. We'll focus on what makes their Vinci architecture different from GPUs and TPUs and why it's designed for large-scale AI training and inference in modern data centers. You can think of these three accelerator platforms as different personalities for deep learning. NVIDIA GPUs are the generalists, very flexible, with broad framework support, and able to handle almost any workload from research experiments to production. Google TPUs lean into scale and efficiency. They're strongest when your model fits a graph, compiled cloud-native workflow, especially for large, steady training jobs. Huawei Ascend focuses on dense data center deployments with high FP16s, BF16 throughput, and tightly integrated server hardware. Modern AI accelerators are built as three tightly connected layers. At the top, many small compute engines act like factories, repeatedly multiplying and adding tiles of tensors. Just beneath, fast on-chip memory feeds those cores at extremely high bandwidth before anything spills out to HBM. At the base, high-speed I/O links the chip to CPUs and other accelerators. Deep learning performance depends on balancing all three: compute, memory, and interconnect. Most deep learning accelerators follow the same core design ideas. They assume the workload is dominated by matrix multiplications and convolutions, so the hardware is heavily specialized for those patterns. They invest heavily in on-chip buffering to keep data close to the compute units and avoid slow trips to external memory. And they're optimized around low-precision formats like FP16, BF16, or INT8 to maximize raw throughput while keeping accuracy acceptable. Huawei's Ascend chips are built around something called the Vinci core. You can think of it as a unified AI engine with three specialties working together. Vector units process long numerical lists, tensor units accelerate matrix multiplications for deep learning, and scalar units manage control logic and coordination. Together, they execute AI workloads efficiently under a single, coherent programming model. Like GPUs and TPUs, Ascend splits work between scalar and vector units. Scalar units handle the bookkeeping, control flow, index calculations, and deciding which data each core should touch. Vector units provide the muscle. They apply the same simple operation to many values at once, things like ReLU, pooling, parts of layer norm, and reductions, such as sum or max. Because deep learning layers are mostly vector-friendly, good hardware keeps scalar overhead low and vector units busy. Tensor units are the specialized engines that do most of the heavy lifting in modern accelerators. You can think of them as hardware built specifically for fast matrix math. Instead of doing one multiply add at a time, they process entire tiles of a matrix in parallel, especially in FP16 or BF16, powering large-scale deep learning training runs. Accelerator memory behaves like concentric speed zones around the compute units. At the center are registers and tiny SRAM. Extremely fast, but very small. Around that, shared on-chip memory feeds entire warps or cores. Further out, HBM or DDR holds full batches and model weights. The key is data flow. Move data inward just in time, reuse it as much as possible, and stream new data with DMA, so transfers overlap compute instead of stalling it. You can think of the Ascend stack as a translation pipeline. You write models in familiar frameworks like PyTorch, TensorFlow, or MindSpore. Those calls flow through Huawei's SDKs and libraries, which provide optimized kernels and APIs. Next, the CAN toolchain compiles your graph, performs operator fusion and layout optimization, and emits instructions tailored for Vinci cores. Finally, the 910C or 950 hardware executes those instructions efficiently, giving you end-to-end acceleration without rewriting model code. CAN is essentially the Ascend compiler toolchain that sits between your model code and the NPU. Your framework exports a computation graph, and CAN rewrites it. It fuses operators, chooses kernels, and tiles tensors to match the Vinci cores. Profiling tools then measure where time and memory are spent, so you can refine the hotspots. The result is an optimized executable that drives the hardware close to peak throughput. Ascend isn't a separate programming world. It's integrated into the frameworks you already use. With the Torch NPU plugin, most PyTorch code can move over by just changing the device string and adjusting a few unsupported ops. The Ascend TensorFlow adapter works in a similar way for existing TF graphs. Mindspore is Huawei's native framework, giving the richest access to Ascend features. And OnX acts as the bridge, letting you convert models between these ecosystems. CUDA gives you the most generic, flexible path. It's the de facto standard on GPUs, runs on a wide range of hardware, and has a huge third-party ecosystem. You write normal, often dynamic, framework code, and CUDA kernels execute it with very fine-grained scheduling. Ascend is more specialized. It's tightly integrated with Huawei appliances and relies on a unified graph compiler stack, so you depend more on framework plugins and supported graphs than on writing low-level custom kernels yourself. The next big difference is where and how you can run each platform. Google TPUs are tightly integrated with Google Cloud. You get managed infrastructure, pay-as-you-go pricing, and workflows centered around TensorFlow, JAX, and XLA. Ascend aims at the opposite end of the spectrum, private data centers and on-prem deployments, using Huawei's CAN stack and Atlas appliances. So think managed cloud service for TPUs versus hardware platform you own and operate for Ascend. When you choose hardware, think along two axes: how locked in you are to a vendor ecosystem and where you need to deploy. NVIDIA is the most flexible. It runs almost anywhere, with broad framework and tooling support, though often at higher cost. Google TPUs are ideal when you're already committed to Google Cloud and need massive managed scale. Huawei Ascend is strongest for controlled, on-prem environments where you can standardize around an integrated appliance. In this module, you saw how the Vinci architecture drives matrix-heavy deep learning with specialized tensor, vector, and scalar units, and how the CAN software stack connects PyTorch and TensorFlow to Ascend NPUs. Next, you'll start porting your existing GPU models and validating their performance and correctness on Ascend.